Okay, we were simplifying radicals, right? I showed you the trick. Couples go out, singles stay in, right? So last example we looked at was a big one. If we wanted to simplify the square root of 4320, we broke 4320 up into its prime factors, and what we found was we had couples. I'll make this a little smaller. We had a couple of twos, and a couple of threes, right? And then we had some singles. I had a single 2, a single 3, and a single 5. And so we write our answer then. Remember that whatever we have a couple of, so a set or a pair, we have a pair of 2s, then I get one factor of 2 outside the radical. Another couple of 2s, there's another 2 outside the radical, and then a couple of 3s gave us our third outside factor. The inside factors, there's just a combination of all the singles, right? The 2 and the 3 and the 5. And so if we simplify that, 2 times 2 times 3 is 12, and 3 times 5 times 2 is 30. And so the simplified radical is 12 radical 30. Okay, no big deal. Now what we didn't get to is how do we simplify quotients of square roots? So what about, or also one other thing too, what about a product of 2 or more radicals? What are our options here? Let's look at one of these two. Because you can do this a bunch of ways, but let's try to be smart about this. What are our options here? And what you may have been told in the past, we're going to do a little different. I mean, we could multiply 2 times 10 times 15 because we have a property of radicals. The square root of A times the square root of B is what? Square root of A times B. So we could, if we wanted, we could rewrite this as the square root of 2 times 10, which is 20, times 15, which is 300, and then just start from scratch. It's not really a smart idea, though. How come? It's already factored. Yeah, look, we've already got this thing factored. We've already got this number in the middle broken into a 2, a 10, and a 15, right? So we could just set this up, and we could take each of these separately. We could take the 2, which is already done. That one's already factored. What about the 10? Okay, there's a 2 and a 5. And then 15. Okay, and we could just do it that way, right? Now we could look at we could try to find our couples and our singles. So we've got a couple of 2s. We've got a couple of 5s. And we've got a single 3, right? So we can go straight to our answer. What's the answer? So we're going to get, now I have a couple of 2s, so what goes outside? 2 times 5 times the square root of 3, right? And so that just gives us 10 radical 3. And would it have worked to make it the square root of 300 and then break that down with a factor tree? Sure, it would have. But why do that? Why not just make 3 separate factor trees and just, combine the factors, right? Sure. A little bit easier. Okay, already some of the work's done for us. Okay, what about something like that? If we've got a square root of 36 divided by another square root, what can we do? Yeah, we will. So this one's pretty easy, isn't it? Right. This one just works out to be, what's the square root of 36? So this one's just 6 over, which reduces to? Okay. Well, what about something like that? Oh, God. So what are we going to do?
Tree.
So we got to, right, so we got to make a factor tree. Now, we have some options. One thing we could do, one thing we can always do if we want to, we can always combine those two if it's helpful. In this case, it's not, but it could, in some cases, be helpful. like, let's just take another one for just an example, and then we'll come back to this one. What if we had, for example, the square root of 100 divided by the square root of 50? Okay, in this case, it really would be helpful if we wrote this as one big square root, 100 divided by 50. And that's okay to do. Just like we had this property that we referred to a second ago, the square root of a times the square root of b equals the square root of a times b. What's the corresponding property you think for quotients? There you go. So we'd say that the quotient of square roots equals the square root of the quotient, right? So we could write that as one big square root. And that makes this a lot easier, because what does 100 divided by 50 break out, or simplify to? And that's our answer, right? So sometimes that's really helpful, but sometimes it's not. In this case, in that last example we did, would it have been helpful? We could have broken the square root of 36 over 16 up into the square root of 36 sixteenths, and that does reduce. What's that reduce to? 9/4, I guess. Yeah. Right. So I mean, that would have helped a little bit, I guess. Then we could have just broken that up into square root of 9 over square root of 4. But did it really help? I mean, we had an answer anyway. So in that case, it wasn't really necessary, right? That case, very helpful. In this case, it doesn't work at all. There are no common factors between 169 and 50, right? So we're sort of stuck with it the way it is. So then what's our rule? Well, we're going to try to simplify the top and the bottom as far as we can, and that's really important that you do that. That makes the numbers we work with a lot smaller. So on the top, square root of 169 is 13, right? And that's a pretty simple factor tree. If we do 169, the only factors of 169 are 13 and 13. So we get a couple right there. What about the square root of 50? If I take 50 and break that up into factors, what are the factors? 25 and 2, and 25 is, so we see we got a couple and a single. And you don't have to write the factor tree out of this. Probably, maybe after you do a couple of these, you can even just see that from the beginning, that 50 is going to break up into 25 and 2, and 25 is a perfect square, right? So we're going to get a 5 outside and a 2 inside. Okay, but we're stuck with a radical in the denominator. Okay, so we got to get rid of that, because that's not, we simplified form for something like this would be a rationalized denominator. So the denominator can't be irrational. What do we do? Do you remember the strategy for that?
I don't know. Isn't that the 10th basement?
Yeah, right. So you can't. So right. So you can't have a tent in the basement. Right. Yeah. So what are we going to do? What are we got a tent in the basement. What do we do?
You gotta get the tent out of the basement.
You gotta get the tent out of the basement. Absolutely. How are we going to get that tent out of the basement?
Oh, do you multiply it by the radical 2?
Yeah, you do. Okay. So here's what we do. So remember, we can multiply. What can we do to a number and not change its identity? Right. There's two things. When we can multiply by 1, or we can add 0. We don't want to change the value of our answer, do we? Right? If I put this into my calculator as a decimal, when I'm all done, the simplified answer that I get, if I put that into my calculator, how should those decimal answers compare? They got to be the same, right? So we can't do anything that's going to change the value of our answer. So we can only multiply by 1 or add 0 in order to preserve the identity, right? So we're going to multiply by 1 in this case in the form square root of 2 over square root of 2. Why are we doing that? Well, because what's the square root of 2 times the square root of 2? 2, right? If we multiply a radical by itself, what are you really doing if I multiply a radical by itself? If I take the square root of 2 times the square root of 2, isn't that just the square root of 2 squared, right? And squaring a square root undoes the radical, right? So there's our strategy. So on the top then, we end up with 5 times 2, right? Or on the bottom, sorry. 5 times 2. On the top, we get 13 times the square root of 2. And so our final answer is 13 radical 2 over 10. Now, you can't just write that down and always assume that's the simplified answer, though, because sometimes there's more, I'm like, maybe sometimes we could simplify that fraction. We can't this time, but sometimes we could, right? Does that make sense? Okay. All right, so that brings us to the next stage, which is why did we review that stuff? Well, we reviewed that stuff so we could solve problems like this. Okay, so let's stare at this for a second, and we want to be strategic. Now, I know we're practicing solving quadratic equations by isolating x, right, using the square root property. But we won't always be doing that. At the end of this unit, there's going to be a bunch of different types of quadratic equations I'm going to give you, and it's going to be your job to pick out the best strategy. Okay, so why are we using the strategy of isolating x here? What is it about this one that makes this an easy one? Later on in the unit, you're going to like this guy. These are the easy ones. What's easy about this? What is it again? So I've got something squared. I mean, that's, okay, I'll buy that. But easier than that, how many x's are there in this? One. Right, so we can point to a single x, and so we can isolate it by reversing order of operations. That's all I'm asking for. So in this case, later on, we're going to be dealing with quadratic equations that have x squares and x's. And then we got to do something different. But that's the next step, right? So for this one, we just reverse order of operations. So what's the first step? Subtract 10. So step 1, subtract 10. So what, negative 196? What's next? Multiply, divide by negative 2. Now, why is it that we can't distribute this negative 2? It doesn't work. If I were to distribute the negative 2, that's not an isolating step, that's a simplifying step, right? Okay. And the order in which I have to simplify, that's top down, I can't multiply and divide until after exponents. And I got an exponent, right? So the red flag here you're seeing, when you have the idea to distribute that negative 2, the red flag is, no, I can't do that because the quantity is being squared. I can't distribute over a quantity that's being taken to a power, right? So I wouldn't want to anyway. Remember, my goal here is not to do something to the left side other than just taking things away, just paring it down so I end up with an x. Right? So we divide both sides by negative 2. Those cancel, that's good. So on this side we get, what, 98? Okay, now what? Now we square root both sides, and that's fine. Does that negative sign seem weird? It's not. It's not, because I've got a variable in there, right? We've just got something behind there that we don't even care about. We just know that we're going to undo the squared by square rooting both sides, right? It's okay to do. So that cancels the squared, and we end up with negative 2x plus 3 equals what? If I square root both sides of an equation, what do I have to include? Plus or minus. And then I've got the square root of 98, right? Okay, so we got to figure out what the square root of 98 is. Let's take a second and just do that. So if I break 98 down into its factors, what do I get? Okay, so I get 2 and 49. 49's looking good, right? 49's just a perfect square. That's just 7 squared. So we got a couple of 7s, single 2. So this looks like 7 radical 2, right? Okay. All right, so now what? So we're all the way up to here. Then we finally get up to what used to be in parentheses, right? What do I do? Subtract 3. Okay, so if I subtract 3 from both sides, where am I going to put the negative 3 on the right side? I always want to put it out in front of the plus or minus, right? So we get negative 2x equals negative 3 plus or minus 7 radical 2. Okay, now let's go back for just a second. Let's go back to one of our earlier examples, because we did some stuff like this earlier. Didn't we? Thought we did. Oh, maybe we didn't. Okay. Okay, so here we are. That's all right. So now what? Okay, divide by negative 2. Right, divide by negative 2. Now I want to draw a distinction here between this kind of problem and maybe a little bit easier one. This is a little tougher because the radical didn't simplify. So normally, like we might sometimes end up with an answer, what if this had been a perfect square on the other side and we didn't have a square root of 98, we had a square root of like 49 or something instead, right? Then we might have had an answer instead. We could have had an answer like negative 2x equals negative 3 plus or minus 7. Okay? So here's the rule then. If both of these numbers easily combine, so if neither one of them is irrational, then the way you could do this is you could just divide each side through by negative 2, and that represents both of your answers. All you'd have to do then to get your answers is say, if I take the plus sign, what would I get? I'd get x equals negative 3 plus 7 is 4 over negative 2. So what's 4 over negative 2? What does that simplify into? Negative 2. So there's one of my answers. Or if I take the minus sign, I'd get negative 3 minus 7 is negative 10 over negative 2. What does that simplify into? Positive 5. Okay, so those would be my two solutions. Okay? If that's the case, if the two numbers on top are both rational numbers, they're both integers that combine easily, then just make one big common denominator and solve for the plus and solve for the minus separately. That's pretty easy to do, right? But that's not what we got here. What we got here was two numbers that don't combine easily. So making a common denominator here really doesn't make a lot of sense because I'm not going to be able to combine the numbers on top. So if the plus or minus term, the one that's being added and subtracted, is irrational, then what you want to do instead is just divide each term separately by negative 2. Okay, but let's focus on this part for a second. What is 7 radical 2 divided by negative 2 simplify into? Well, you can't really cancel anything, but a positive divided by a negative is a negative, right? Okay, well, does that make sense to do if I've got plus or minus negative 7 radical 2 over 2? Isn't that negative kind of superfluous? It doesn't do anything, right? I mean, all it's doing is, we're going to take both signs anyway, so why make it negative, right? You can make it easy on yourself, and always, if the second term includes a radical, so if it's irrational, instead of dividing by the negative, just divide by the absolute value and make it positive, right? So instead, we could do this. We could just divide the second term by 2 and go right to our answers. See what I'm saying? Okay, so here's kind of the rule that you can put in your notes, and I'll put this in the notes online too, if you don't wanna write it down, if you know where to find it. If the plus or minus term of your answer contains a radical, always divide the plus or minus term by a positive number, so by the absolute value of whatever the number is that's in the denominator. It just makes life a lot easier. Okay? Make sense? Okay. You got a little time here. Try, how much time we got?
13 minutes.
13 minutes. Is that right? Yeah, 13 minutes. Why don't you try to do, I want to see you do a couple problems from everything. Right, so you've done, probably you guys have already done most of the prime factorization ones. Those are probably done. I want to see you do a problem or two from the quotients of radicals, and then try a couple problems from all parts of the next assignment, the last assignment, the one on solving by square rooting both sides. Okay? All right, have at it.